Today I'm going to talk to you about polarization. Most sources of light, which are transverse waves, emit unpolarized light, which means the oscillations take place in randomly orientated directions, perpendicular to the travel of the wave. When light is emitted by a source, it is as a result of the electron transitions within the individual atoms of the source. These transitions occur rapidly, and each gives rise to a wave for a short time. The amplitudes of vibrations are equal. Unpolarized light consists of components that are polarized in all possible directions perpendicular to the direction of the propagation of the wave. Each of these polarization directions can be resolved into components along two mutually perpendicular directions. Thus, an unpolarized beam can be thought of as two plane polarized beams of equal magnitude perpendicular to one another. Different ways of showing this are shown in the diagrams. Polarization is the filter of the light so that there is only one dimension. The polarizing filter absorbs about half of the energy, as the filtering is as a result of long polymers in the material all being aligned the same way, and so only the light that aligns with the filter will not be absorbed. The chance that any single photon will be passing through depends on how close its polarization is to the angle of the polarizer, and as the photon orientation is random, the amount of photons absorbed will be about half. This is shown in the diagram by having slits in a polarizer, and only, as you can see, only one dimension is allowed through. There are different types of polarization. The most common type is linear polarization. They absorb all the energy except in one plane, as shown in the diagram. This reduces glare and reflections and makes colours more vivid. The first diagram is a practical example, with two pieces of string being shaken in different directions to create two waves in different directions. Only the blue string is allowed to go through the slot, as only that one has the same polarization as the polymers. In the second diagram, the top one, the first filter of both of the second diagram is vertical, and so only the vertical beam is allowed through. In the top one, the filter is again aligned vertically, and so the light is allowed to carry on. However, in the second one, the filter is aligned in the opposite direction, and so the light is absorbed into that, and so it won't go through. The second type of polarization is circular polarization. Circular polarization can be thought of as two dimensions, one horizontal and one vertical, moving a quarter of a phase out, pi over 2 radians. This results in the maximum and minimum points on the two dimensions matching up with the precise point when the dimension is at 0. This results in a helix being formed. In the bottom diagram, you can see that the peaks align with the others wave point being at 0, and the resultant wave that is formed is shown in the animation. Circular polarization occurs in nature. Some animals, such as the scab beetle, and some crustaceans, such as the mantis shrimp, can reflect light which is at least partially circularly polarized. In these cases, the underlying mechanism is the molecular level helicity of the chitinous cuticle. Examples of these animals are shown in the pictures. Water-air surfaces provide another source of circular polarization. Sunlight that gets scattered back up towards the surface is linearly polarized. If this light is then totally internally reflected back down, its vertical component undergoes a phase shift. To an underwater observer looking up, the faint light outside is therefore partially circularly polarized. There are other types of polarization in different materials. Optically active substances actually rotate the polarization of the light passing through them. This is shown in the first diagram with the rainbow colours. Refringent materials refract light by different amounts depending on its polarization, shown in the block. An example of this is the mineral calcite, which produces clear double images by splitting the incoming light into two streams with complementary polarization. You can see in the calcite crystal that two pencils are shown. There are more examples of polarization and uses. So one of the most common uses are polarized sunglasses, which reduces the light coming to your eyes, so reduces the chance of eye damage. This means these are especially used by fishers, as shown in the picture, as it makes the fish much more easy to see. It's also used in liquid crystal displays, photography, as it reduces the glare and reflection and intensifies colours, again shown in the picture of the fish. Quantum cryptography, decoration, as it can produce beautiful effects, shown in the top picture. And most recently, there's been a great increase in the use of it for 3D effects. 3D polarized glasses are aligned at right angles, so that light is emitted by one glass is blocked by the other, in a similar way to how red-blue glasses worked before, although it lets all of the light through, and so the colour is much more vibrant and true to real life. This is shown in the diagram with the dinosaur. Only the vertical rays are allowed in one way, and only the horizontal rays are allowed in the other way. I hope you have enjoyed my talk on polarization.